Welcome back. In this section, we'll be talking about functions, and before we get there, we'll need to talk about the more general idea of a relation. For a relation, we have two collections of objects or things. One is the domain. This is the collection of all of our x values. And the other one is our range. This is the collection of all of our y values. And what a relation is, it's just a set of x and y points where x values come from our domain and y values come from our range. So here I'm saying x and y are collections of objects. Those usually are numbers, at least in the class that we're going to be dealing with, but they don't have to be. So an example of a relation where x and y are not numbers would be this example, where x is the set of all the countries and y is the set of all the cities, and I make a relation where I'll have that x and y point if city y happens to be located in country x. So, for example, Canada, comma, Victoria, that's part of my relation because Victoria is inside of Canada. Same with USA, comma, Seattle. Seattle's inside of the US, so that's a point. But Canada, comma, Seattle, that's not a point in my relation because there is no Seattle in Canada. For a relation, there's no restrictions on reusing x values or reusing y values. So, for example, we know that there's a Canada, comma, Victoria, but there's also a Canada, comma, Vancouver, and there's also a Canada, comma, Toronto. The x value Canada gets reused multiple times with different y values. And in a relation, you can also have y values being reused. We know that there's a London in Canada, so we'd have a point Canada, comma, London. We also know that there's a London in England, so there would be a England, comma, London as well. So x values can be reused for a relation, y values can be reused as well. We're going to see that a function is just a special kind of a relation where there's a little bit of a restriction on repeating things, but we'll talk about that in just a moment. Before we get there, a few things about displaying or expressing relations. So the first way, and this is really only makes sense if you have a small finite number of ordered pairs, is to just list everything. So here my relation only has 4 ordered pairs in this example, so it's easy enough for me to list them all: 1, 1, negative 1, 1, 2, 4, negative 2, 4. All my x values, the 1, minus 1, the 2, and the minus 2, that's the collection of objects that are my domain. And for my range, I only have 2 different objects, 1 and a 4. Those are my 2 numbers that got used as my range. The fact that I reused my y values here, I'm not indicating that in my range. I'm not going to write 1 twice and write 4 twice. Whenever we're listing things in curly brackets, whenever we're listing a set, we only list unique objects. So 1 and 4, those were the different y values that we saw. The fact that 1 got used a couple of times, I'm not going to indicate that in my range. That's not how we do things. So like I said, this really only makes sense if you have a finite number of pairs and it's a small number of pairs. If you had a small number of pairs, you could maybe do a couple of other ways of expressing a relation. One might be to show it as a mapping, where we've got a circle with all of our x values in it and a circle with all of our y values, and we show who is a pair by showing an arrow going from an x value to a y value. So we can see that 2 maps to 4, so in other words, 2, 4 is a pair in that relation. Again, this only really makes sense if we have a small number of pairs. One other option that we do have is to express our pairs as a graph, just literally plot them on the x and y plane. In this case, easy enough to do since there's only 4 points, but if you had lots of points, maybe those points would connect together to make some sort of a curve. So for example, if you remember graphing a straight line back in chapter 2, that straight line is a collection of x and y points, so that means that that straight line is a relation. So whenever we're graphing things on the x and y plane, that's a relation. You also will typically see, at least in this class, relations expressed as equations. So when I say y equals 3x, that's a relationship between y's and x's. That is a relation. Now, as far as functions go, every function is a relation. It's just a special kind of relation, and it's one where the x values don't get reused. Or in other words, every time we have a single input, a single item taken from our domain x, then it's going to produce a single output, a single value coming from our range y. So for example, the previous relation, the x values were -2, -1, 1, and 2. Every x value got used exactly once. No x value got reused, which means that that relation would also be considered to be a function. However, our very first relation, where we had a pair Canada, Victoria, and where we would also have a pair Canada, Vancouver, and also Canada, Toronto, because the x-coordinate here is being reused, then that would mean that this relation would not be a function. A couple of other things just to mention, a little bit of notation. Typically, when we're talking about a function, we'll name it with a single letter, because usually when we're expressing our function, we're going to do that in the form of an equation. So here, when I write something like y equals f and then in brackets x, I'd read that as f of x, and that's telling me that my function's name is f, and that x is the input for my function, and that y is the output for my function. We could also say that y is the dependent variable because the value for y will depend on whatever you've put in for your function. It'll depend on x. The x value, we'll call that the independent variable. That's the one that we can change, and when we change our value for x, it will give us a different or new corresponding value for y. Sometimes you'll also hear x being referred to as the argument of your function. And so you'll see that for things like when we're talking about a square root function and somebody's referring to the thing that's inside the square root, somebody might call that the argument of your square root. Okay, so we have an equation, and here the equation is y equals 3x, and the question we have is y a function of x, or is x a function of y? Maybe both, maybe neither. There's no guarantee that when you have an equation that it's going to be a function. So when we ask ourselves the question of is this a function, the question is, if it's a function of x, that means for every x, do we get exactly one y? So if we're taking a look at this equation, and if you're imagining putting in one value for x, and then squaring it, you would still have one single value. And then if you multiplied by 3, you'd still have one single value. So I would say yes, for this one, it is a function, and it's because each x corresponds to exactly one y. On the other hand, if you ask the question about is x a function of y, if we pick one y value, are we going to get only one x value? The answer would be no. So for example, if I were to pick y as 3, and I said, what's the x value that I would get if y is 3, then we'd say that 3 is 3 times x squared, or 1 is equal to x squared, or in other words, x is plus or minus the square root of 1, which is just 1. In other words, for one y, we get two different values of x. So because every x corresponded to exactly one y, if you put in one x value, you're only going to get one y value out using this equation. Then you can say that y is a function of x. But the reverse is not true. If we picked one y value, we don't only get one value for x, we get more than one value. So that's telling me that x is not a function of y. All right, a few other little things about this. Again, the domain is our set of all the values that are our inputs, and the range is the set of all of our values that are outputs. You will sometimes see a little bit of a notation format like this at the start, where we'll have a function definition of what is our function expressed as an equation. Here, f of x is equal to x squared. So this is telling me that if I put in a value for x, that to find the value for y, I'll square it. But then we've got this little curious thing at the beginning, and this is telling me what sort of x values I'm using and what sort of y values I'll be getting out of it. Here, the sort of funny script letter R, that's a symbol for the real numbers. So this is telling me that for my function f, it's going to have real numbers as its input, and it's going to have real numbers as its output. So when I'm giving this little definition, of course, real numbers as its input, that's telling me what the domain is. So if I wanted to know what the domain is, I would say it's all the real numbers. The kind of numbers that I'm having as my output, that's what we call the codomain. So this is telling me the sort of numbers I'm expecting to get are real numbers. So I would say my codomain is the set of real numbers. But the difference between the codomain and the range is this. The range is the kind of numbers you would expect to get coming out of that function. The range is the actual numbers that you get coming out of this function. And if you remember from your previous math classes, if you were to graph that function y equals x squared, it's a nice little parabola centered at the origin, opening upward. For that one, the actual y values are only 0 and larger. So although the codomain is real numbers, it's going to be real numbers that come out as y values for our function. The actual range for our function would just be the values that are 0 and larger. So first thing that we'd want to do when we have a function, or one thing that we might want to do when we have a function, is evaluate it. And again, this is probably old news, at least the evaluating things numerically. When we evaluate a function, we're replacing x, our independent variable, with a value. And then we're finding out what's the corresponding value for y. So if our function was f of x equals x squared, if I say please find f of 3, well, that's replacing the x with 3, and we'd get 3 squared or 9. So if somebody says, what's the value of my function when x is 3? Then the answer would be 9. This is something else also to talk about. When we're referring to values of functions, we're always talking about the y value. So when somebody says evaluate the function, we're trying to find out what is the y value, what's the dependent variable's value. Now here, where the one little plot twist that we have is that when we're evaluating a function, we might be doing so by replacing x with a number, but it might also be that we're replacing x with some kind of an expression that maybe involves x or maybe involves other variables. But the idea of how we evaluate is exactly the same. So when I was looking at f of x being x squared, and when I was finding f of 3, I just did that by replacing the x in my function with a 3, and I got 3 squared, or 9. If I have the same function, f of x being x squared, and I want to have f of a plus 1, that's telling me that what I need to do is replace my x with a plus 1. So instead of x being squared, it's a plus 1 that's being squared. The one thing to note here also is that as I'm doing my replacement, just as I did above, I'm replacing things in brackets, because whatever the input is, the function has to square all of that input. So I have to make sure that since a plus 1, since all of that is my input for this function, that all of a plus 1 is getting squared. If I didn't have my brackets around it, if I just wrote a plus 1 squared as I currently have it, it would only have the square attached to the 1. And of course, the square needs to attach to that entire expression of a plus 1. So I always am going to make sure that when I'm evaluating functions, I'm going to evaluate using brackets. And now I'm just going to do a little bit of expanding and simplifying, and then there we go. So a plus 1, when we square it, that's a plus 1 times a plus 1. And when you expand, you'll have a squared, you'll have another a, and 1, or a squared plus 2a plus 1. So something to notice here, of course, when you've got a function and you evaluate with a number as your input, you get a number as your output. When we evaluated with something involving the variable a as our input, we got something involving the variable a as our output. And that shouldn't be too terribly surprising. The kind of output that we get depends on the kind of input that we put in. All right, so let's do a few examples where we've got a nice little polynomial function and I want to evaluate it. And so some of these are going to be evaluating it purely numerically. Some of them are going to involve variables. So let's start with the first one. We want to find out what's f of 0. And to do that, we're going to replace all of the x's in brackets with 0. So I would have 3 times 0 squared, which is 0, minus 2 times 0, which is 0, plus 1, or 1. And again, I had a numerical input. I'm expecting a numerical output, and that's exactly what I find. All right, second one up. Here, this is two things sort of going on. We have f of 2, so we're going to evaluate our function at x equals 2. And you can see that there's a minus in front, which is another way of saying we're looking at negative 1 times that value that we'll get. So when I write negative f of 2, it's not that the 2 going into my function is negative, it's that the entire function is going to be multiplied by negative 1. So I'm going to evaluate what f of 2 is, then multiply by negative 1 at the end. And to find f of 2, I'm going to replace all of my x's with 2's. So 3 times 2 squared minus 2 times 2 plus 1. And I'll get negative 9 as my result here. So negative of f of 2 is 9. Last one on this slide, I have f of 3a, so here we're evaluating involving 3a, so I've got an expression with a's as my input, and so when I evaluate and I replace all of those x's with 3a's, then I'm going to get something with a's as my output. So let's see what we get. So again, we're making sure that when we replace all of our x's with in this case 3a's, that we're doing our replacing in brackets. Because it's not just the a that's going to be squared, the 3 needs to be squared as well. So here, let's clean that up. 3a, when I square it, 3 squared is 9, a squared is a. For the second term, 2 times 3, that gets me 6. And then my little one last bit of doing things, 3 times 9 is 27. Okay, two little last ones to do here. So this one, f of x plus 2. So the one mistake that people will often make when they look at something like this is they'll take the original function, 3x squared minus 2x plus 1, and they'll just say, oh great, I'll just add 2 on at the end, except that's of course not correct. That is not what we're looking to do here. Instead, what we're looking to do is to take our original function and replace all of the x's with x plus 2's. So our original function was 3 times x squared minus 2 times x plus 1. And instead of having the x being squared or the x being multiplied by 2, it's going to be x plus 2 that's getting squared, and it's going to be x plus 2 that's getting multiplied by 2. So I have a little bit of work to do here as far as the expanding goes, But again, notice that the idea is still the same as before. We're just replacing our input by whatever our input of the function is, in replacing it in brackets. So replacing all of our x's with x plus 2's. And then the only thing left to do after this is just to clean things up by expanding and then simplifying. So let's do that. We've got 3x squared plus 12x plus 12 minus 2x minus 4 plus 1. And I've got 3x squareds. For x's, I have got 10x. And then for constants, I've got 9. So again, kind of not a big surprise here, and we've seen this sort of happen 3 times now, where when we are evaluating with a number as the input, we get a number as our output. We evaluated with something with a's as our input, we got something involving a's as our output. And now we evaluated with involving x, we get something involving x as our output. So, okay, no surprise here what we should expect to see then for f of x plus h. For this, since we have inputs involving x's and h's, then our output should also involve x's and h's. And we'll do exactly the same thing that we did in the last example, where we're going to take our function and replace all of our inputs with x plus h. So 3 originally was x squared, minus 2, originally x, and then plus 1. We're replacing our original x with x plus h, and then we will expand and simplify. So when we expand, we'll get 3x squared, 6xh, 3h squared, minus 2x minus 2h plus 1. And as I said that we would expect to see, we evaluated our function with x plus h as our input, and we got an output that involves x's and h's.